Okay guys, welcome back to my channel. Now today we'll be discussing something very important in mathematics for my viewers all over the world. Okay, now if you're taking the topic rather calculus in mathematics, now this topic, integral functions, is a very core aspect of calculus in your examination. Okay, now what are integral functions basically? Now quickly, the heading we'll call it integral. Okay, integral functions. Now there are various integral functions you come across while studying, but for this class we'll be talking about the guy we call gamma function. Now what is a gamma function? Basically these are functions under calculus, okay, that have a particular pattern. So instead of trying to solve it the normal conventional way of integrating functions, we then compare the function to what we call a gamma function. If it fits the description, then we apply the gamma function principle. Now, how does the gamma function look like? I'll give you on the board now. Okay. Now, first things first, the symbol for gamma function is a capital letter for gamma, which is written like R. Okay. So let's say, for example, the gamma function of x, okay, is the integral. Now you must take note of the limits given in the question. For it to be a gamma function, the limit must be from 0 to infinity. Okay, so the gamma function of x is basically the integral from 0 to infinity of, now we're going to say t, okay, to the power of x minus 1 exponential minus t dt. Now you're going to observe what's occurring here, okay? Now the gamma of x is equal to the integral from 0 to infinity of a variable. This variable t can be anything. It can be y, it can be u, it can be a, b, c, d, any variable at all. Now we have x minus 1 here, meaning whatever you have here, you're going to minus 1 from it to get the power for t. Take note, x is a number. Okay, x is an integer, is a number basically. Can be 2, can be half, it's a number. Okay, so we have a number here, but it's reduced by 1. So if you have gamma of 2 here, for example, you're going to have 1 here. You know why? 2 minus 1 becomes 1. If you have 5 here, you're going to have 4 here. Okay, now the variable you have here must also act as a power to an exponent. Okay, so when your expression looks like this, then we say that guy is a gamma function. So you are integrating this function with respect to t, the variable. Is that clear? So once the function comes in this format, then we call it a gamma function. Now easily we solve gamma functions in different manners, okay? But the easiest way we apply is we apply the factorial method. Now I'm going to show you how we relate the gamma function to the factorial method so we can start solving some basic questions from there. So please, if you're just seeing my channel, kindly subscribe, okay, and click on the notification bell on your app, so whenever I drop videos, you'll be notified as to when I drop the videos. This is going to be a series of videos, okay? So we're going to do all the integral functions and also start what we call the Fourier series, okay? So those in university levels or advanced mathematics, this video is what you shouldn't miss. So let's go back to the video. Now quickly, for us to relate this to the factorial pattern, I'm going to do something quickly. If the gamma of x gives us this, how about we express the gamma of x plus 1? If the gamma of x produces this function, how about we express the gamma of what? X plus 1. Now let's see. The gamma of x plus 1 is going to be equal to, again, the integral from 0 to infinity. Remember, the variable t. Remember I said, whatever you have here, you're going to have it less than 1 over here. Recall, we had x here, and then we had x minus 1. So we remove 1 from x. So we're going to remove 1 from this guy to be here. So we're going to say x plus 1 minus 1. Okay? And then we have exponential. This remains as minus t because there's no x here. Okay? And then we have dt. Now simplifying further, the gamma of x plus 1, okay, should become the integral from 0 to infinity. Now, what is 1 minus 1? That gives us 0, okay? So we have t to the power of x, okay, and then exponential negative t dt. So this means the gamma of x plus 1 is equal to the integral from 0 to infinity, the variable raised to power x. Now listen, x, as I said before, is a number, okay? So if you have 3, for example, here, you're going to have 2 in this case now. If you have 3 here, you're going to have 2 for this pattern to work. But if it's a normal, this is a general pattern, okay? Gamma of x. So in that case, you are minusing, but here you are adding. Okay, so yeah, here you are minusing, you are also minusing actually here, okay? Let's not confuse that, okay? So here you are reducing 1, you're also reducing 1 from here, basically, okay? So x plus 1 means, for example, if x is 2, for example, 2 plus 1 becomes 3. So you have 3 here, but here remains 2 in this format. Now, from here, let's try to integrate this function in the conventional manner. Now, how do we integrate this function in the conventional manner? We have two variables, okay? We have two functions here, pardon me, sorry. We have two functions here, okay? So when you have an integral having two functions, you can apply what we call integration by parts. Now, how do you integrate by parts? Recall. I'm going to go over here, okay? So when integrating by parts, what we basically do in that case is, for example, if y is equal to, now for you to integrate by parts, your integral is expressed, for example, as something like this, u dv. Okay, so the integral of u dv is equal to uv minus integral of v dv. So one of the functions will be termed u and the other will be termed dv. So when you integrate u dv, you're going to get uv minus the integral of v du. Now you always take priority to what you give the function u. Now your function u should be the function that when you differentiate, it can easily get to a constant. That's a simple trick you apply. So coming back to our function here, we have t raised to power x, and we also have e to the power of negative t rather. Now, which of these two functions do you agree that when we differentiate and we easily get to a constant? That should be t raised to power x. Remember, x is a number, for example. So let's assume, for example, x is 3, or let's say x is 2, for example. So we have t raised to power 2. Okay? If you differentiate t squared, you're going to have 2t. If you do it again, you're going to have 2. And 2 is a constant. Okay? So that means that I'm going to say, let t raised to power x be our u, and this guy automatically becomes our dv. So we're going to apply this expression here. So uv minus integral of v du. Now quickly, we already know what u is, but we don't know what v is, but we know dv. I'm going to write them out. Okay, so quickly, go over here. U is already t raised to power x. Okay, now dv is already e to the power of negative t. Now let's get du. Now, how do you differentiate? For those who might not be aware of this, or you're new to integrate or to calculate, basically, if you have, for example, t raised to power n, okay, so differentiate this, we're going to do n times t to the power of n minus 1. This is the differential of this expression. So if you have t raised to power x, you're going to have x t raised to power x minus 1. Now, if dv is e to the power of negative t, what then becomes v? So get v, you're going to integrate dv. So the integral of e to the power of negative t remains e to the power of negative t, but divided by, when you differentiate negative t, you're going to get negative 1. That's negative 1 over here. So this can be negative e to the power of negative t. We're going to come over here to continue. Now quickly, we know what u is, we know dv, we know du, and we know v. We're going to plug those values into this formula I gave you. So quickly, we're going to say the integral now, that's the gamma of x plus 1, which is the integral from 0 to infinity of t to the power of x, okay, e to the power of negative t dt becomes, now what will it become? Remember, we're going to be having, from our function we have there over there, uv. Now what's our u? T raised to power x. So t raised to power x, what's our v? Minus, put the minus sign outside here, e to the negative t, okay? Then minus integral again of v. What's our v again? Our v is negative e to the power of negative t and then du. And du is x t to the power of x then minus 1. Okay, now remember, before I continue, when we found du, now this du was us differentiating u with respect to with t. So you can just quickly apply a dt at the end of that differential. Okay, don't forget that. Okay, so this v is separate, this is du, x c to the power of x minus 1 dt, meaning we differentiated u with respect to t. So we can attach a dt over here. Now remember the limit. Okay, it is from 0 to infinity. We're going to also apply the same limit over here from 0 to infinity. But before we do that, let's quickly simplify this expression. So we can say the gamma of x plus 1, okay, that should become, let's see, we have negative t to the power of x exponential minus t from 0 to infinity. Okay, let's put, sorry. And then now minus times minus gives you plus. Remember, it comes out. Okay, now remember that x is a constant, a number, so you can bring out the x. Okay, and then we'll have the integral again from 0 to infinity. We're going to arrange this properly. We're going to have t to the power of x minus 1 then exponential negative t dt. Now observe, what do I mean? First things first, let's apply the limit. Okay, so infinity and then 0. You're going to plug in this, guys, where you see, remember again, very, very importantly, we are integrating with respect to t. So you're going to apply your limit to t, not x, to t. So anywhere you see t, you're going to put infinity and then minus, you're going to put 0. So quickly, what is infinity raised to power a number, for example? Okay, that's basically still infinity. This is like a large, like let's say 2 million or 10 billion raised to power any number. It still gives you a very large number, right? Okay, so that's infinity. Okay, then times, negative sign is here. Now, what is the exponential of negative infinity? Now, this expression from indices can be written as 1 over exponential infinity. Remember, this means a large number. So 1 over e to the power of a large number means at the bottom here, a very, very large number at the bottom, a very large number. Now, 1 divided by a very large number will tend to 0, because ideally, e to the power of negative infinity must always give you 0. Like say 1 over 2 billion, that's 0.00 something, so that's going to 0. Okay, so basically what you have here over here becomes 0, right? Okay, and then minus, put your t as 0, it's going to have 0 again. Okay, so means everybody here becomes what? Becomes 0. So you can just strike this out. We have 0 over here. Okay, now over here we're going to say plus, we have x. Now this integral looks like somebody we know. Who is that guy? This integral over here is the gamma function of x. Observe, we have the same patterns in the structure on the board. So means we have x and then the gamma of x. So this goes to say that the gamma function of x plus 1 is just equal to x times the gamma function of x. So this is very, very important on that gamma function, and we call this the recurrence formula or function. Okay, the recurrence formula of function. Now with this, we're going to express how the factorial method comes about. Now we've seen the recurrence formula for the gamma of x plus 1, which equals the x, then let me write it over here so you can see it better. Okay, so remember, the gamma function of x plus 1, as we just derived, is equal to x times the gamma function of x. Now, since you have this as your recurrent formula, how do they relate? Well, look at the trick here. It means whatever you have here is reducing by 1 to have the input over here. If I have 5 here, I'm going to have 4 over here. 4 and 4. If I have 10 here, I'm going to have 9 and 9. Okay? So going from left to right, I'm reducing by 1. Going from right to left, I'm increasing by 1. So this means that, for example, let's say we are now asked to find the gamma function of x. Remember, from left to right, we are reducing. Okay, so we're having -1, while from right to left, we are having +1. So from left to right, you are reducing by 1, while right to left, you are increasing by 1. That's simple, right? So let's see. So if I have x here, so now I want to put here as my input. I'm going from left to right. I'm going to be reducing by 1. So you're going to have over here x minus 1, okay, and then the gamma of x minus 1. So we're going to have something like this for gamma of x for the recurrence formula. Okay, so now we've seen this. We're going to continue again to get, let's try and get the gamma of x minus 1 and see what we have. Okay, so quickly, the gamma of x minus 1. Well, now remember, from right to left, well, from left to right, we are reducing by 1. So you're now going to have x minus 2 and then the gamma of x minus 2. So this is going to keep on going like that. Okay, so we're reducing further and further and further. And you recall for factorial, n factorial simply means n times n minus 1 times n minus 2 and so on and so forth. So whenever a function or a variable is reducing by 1, that's a factorial term. Now let's see what we mean. Now recall, if we want to put all these guys together now, for example, okay, so we can say that gamma, okay, of x plus 1, which is normally equals to x times the gamma of x. Now what's the gamma of x? It is over here. Okay, the gamma of x is x minus 1 and then the gamma of x minus 1. Now what's the gamma of x minus 1? It's over here again. So I can say the gamma of x plus 1 becomes x first, x minus 1. Now the gamma of x minus 1 becomes x minus 2 times the gamma of x minus 2. So this is a recurrent structure. It is reoccurring, and we can call this guy basically x factorial because this will go on until you get 1. So I can just say it means that the gamma of x plus 1 can just be written as x factorial. So this is how you relate gamma function with factorial. The gamma of x plus 1 becomes x factorial. So for example, the gamma of 5 becomes 4 factorial. Remember, this x plus 1, this becomes x. The gamma of 6 becomes 5 factorial. So this is the first part for this integral function called gamma function. Now we've seen how to relate this gamma of x plus 1 to factorial. Now let's attempt the following simple examples on the board. It says express the following gamma function. Okay, so the first one says the gamma of 6. Remember, gamma of 6 means that x plus 1 is equal to 6. It doesn't mean that x equals 6. No, x plus 1 equals 6. So if x plus 1 equals 6, what should be x? X should be 5. Okay, so it means this should be equal to what? 5 factorial. And what's 5 factorial? That's 5 times 4 times 3 times 2 and times 1. And that should give you around 120. Okay, so with that same manner, we can easily solve this with the speed of light. The gamma of 5 becomes 4 factorial, and that should be 24. The gamma of 1 becomes 0 factorial, and that is 1. The gamma of 7 becomes 6 factorial, and that is 720. So understanding this factorial pattern helps you simplify gamma functions without stress. Now, so in more videos, we're going to see how to relate this to the general formula, and then we're going to talk about the gamma for fractions. Okay, so please remember, try to share this video to your friends and loved ones, your classmates, and try to on the bell button on your phone, and also comment in areas where you have issues. Please and please, if you want to help me or support me, you can send me the super thanks. Okay, it's activated on my channel currently. You can send him or give me the super thanks on the channel, or you can message me through the comment section for support. Thank you and God bless you. See you in the next video.